thank you very much for giving me this opportunity to present recent work here. This work was done in collaboration with Nick Stergioulas at the University of Thessaloniki, and it's part of my PhD thesis, which I defended recently. So luckily, previous talks, both from Professor Kokotas and George Liutas and Theodore Sultanis, have provided motivation enough for this kind of work, but I'll just refresh a little bit on our memory. So a remnant is one of the possible outcomes from BNS mergers. It is massive, it is compact, and at least in the first few milliseconds of its life, it is differentially rotating. And as it was already the case with the now famous detection of the event GW170817, it can inform us on constraining the equation of state, heavy element nucleosynthesis, and help us better understand short gamma ray bursts. And as I said, previous speakers have done have described most of this slide for me. This is just a summary of the different outcomes, and I'll just point out that essentially there are 3 checkpoints which are comparisons of mass values. So the evolution of the binary, of course, it depends on the equation of state and the total mass of the system. So the 3 checkpoints are the threshold mass for prompt collapse, and the second checkpoint is the maximum mass of uniformly rotating stars, and the third checkpoint is the maximum mass of non-rotating stars. So either we will have prompt collapse or delayed collapse scenarios as differential rotation is dissipated, uniform rotation takes over, and the star spins down. So when we want to study merger remnants, of course, our go-to solution are numerical simulations. We want them to be as realistic, as sophisticated as possible, so that they can give us a picture as close to the truth as possible. However, they have a very steep computational cost of several thousand core hours. So it is useful to also explore a complementary approach, which is in essence to consider simplified models by ignoring certain aspects of the realistic configuration. For example, one can assume axisymmetry, stationarity, and neglect thermal effects altogether as a first step. In return, equilibrium modeling can provide, with a fast and wide exploration for the parameter space, the models that we construct can be used subsequently as initial data for dynamical simulations, and it can also give us insights on stellar stability. So this is the method that we employ in this work. And to wrap up this initial motivation part, it is expected that the rotational properties of remnants from binary neutron star coalescences can affect the precise thresholds that lead either to prompt or delayed collapse, and this can have astrophysical consequences. For instance, it can have implications for the development of a possible short gamma ray burst observable in the electromagnetic spectrum, and future third-generation gravitational wave detectors working jointly with observatories and telescopes in the electromagnetic spectrum could go a long way to clarify these issues. So it is useful to try and pinpoint what are the primary factors that affect this threshold mass for prompt collapse. And the way we try to do this here is by looking separately at the effect of the differential rotation law, the cold part of the equation of state, and the thermal effects. So the first ingredient, let's say, is considering thinking about the differential rotation law. And numerical simulations have provided information that the rotational profile actually exhibits a maximum, which is away from the center. And this only mildly depends on the equation of state. You can see, for example, the picture on the right, the olive region, the olive shaded region describes the angular velocity of from a BNS merger remnant. And of course, the widely used monotonic differential rotation law in the literature cannot describe such profiles. Luckily, relatively recently, Uriu and collaborators proposed novel differential rotation laws, and one of which is this 4-parameter differential rotation law, which is the one we used in our recent work. We also tried to decrease the number of parameters by fixing 2 of them. And the rest of the parameters were indirectly tackled by fixing these 2 scenario ratios, λ1 and λ2, which is the maximum angular velocity over the central angular velocity and the equatorial angular velocity over the central angular velocity. And I will just mention that playing around with these 2 values can lead to different types of solutions, as was shown in in work back in 2009 by Anzork and collaborators, Dorota Rosinska and so on. So this seems to be a general feature of differential rotation, and I can elaborate further if there are questions on that. The good thing about these 2 ratios is that one can get information directly from numerical simulations, which means basically read off these 2 ratios from the corresponding rotational profiles obtained numerically. So it's not enough, however, to consider a realistic differential rotation law. When considering remnants, one also has to take into account the angular momentum of these objects. And there are, in the literature, there are empirical relations that were derived from numerical simulations that connect the angular momentum at the time of merger with properties of the progenitor neutron stars or the total mass of the system and so on. So there was one relation in Bauswein-Sterjulas in 2017, and a more recent one by Luca and collaborators in 2021, which is the one we used in our work. And these 2 relations were compared, and we found there a good agreement with each other. And basically, one can be cast into the form of the other by some simple algebra transformation. Moving on, I will just now gather all the ingredients so far and to form our recipe, let's say. So we wanted to construct remnant models, and these models, we wanted them to be massive, which means having masses over 2 solar masses, and we wanted them also to have high angular momentum values. We constructed whole sequences of these remnant models with the new differential rotation law and different values for its parameters. And we did that for 3 cold equations of state, hadronic equations of state. So in the figure on the right, these asterisks denote the remnants that we constructed, and the dotted line serves as a rough indicator for the instability to collapse. So, which means that models to the right of this line are unstable. And the blue triangle marks approximately the intersection of the remnant sequence with the turning point line, which defines the threshold to collapse. And this can all be a little bit more clear if we put our data on an angular momentum versus mass plot. This is actually a repeat of the analysis in Bauswein and Sterjulas 2017, but for a realistic differential rotation law in our case here. So the blue line is the remnant line, and the red and black lines are the turning point lines. They intersect, and this defines our threshold mass. What we find is that our estimated value for the threshold mass via equilibrium models, which I should mention is done with the widely used RNS equilibrium code. So our values agree very well with those from numerical simulations, and the agreement is at the 1% level. And what is interesting, at least I think it's interesting, is that while the simulated values which we took from Bauswein and collaborators, the work in 2020, while these values do take into account the effects of the temperature, our framework is considering only cold equations of state. So this could possibly point that at least for determining the threshold mass for prompt collapse, it is only the cold part of the equation of state that seems to have a key role. Of course, this merits further investigation, but this is an interesting initial finding, because it is also achieved without fine-tuning the construction of particular merger remnants. And moving on to take a look at the rotational profiles of long-lived remnants, and by long-lived I mean remnants that survive some tens of milliseconds and have the time to become quasi-spherical. We found that with the new differential rotation law, a key feature that was already known from a lot of numerical simulations is reproduced. And this key feature is that the angular velocity close to the core is mainly due to the frame dragging of the space-time contribution, which is shown in the picture on the right as the dust line for the light blue line for the most massive model. And it is interesting that there was this feature led to the proposal of a conjecture by Iosif and collaborators in 2017 that merger remnants collapse promptly if the relatively cold and slowly rotating inner region is not possible to be described by a TOV solution. So our findings lend support to this conjecture. And the way that this is supported is that if one again draws the merger remnant model sequences, which are solid lines for the three different equations of state, and finds the intersections again with the turning point lines, but in a plot where we have the mass versus the equatorial compactness, and which is defined as the gravitational mass over the equatorial circumferential radius, then one can notice that there is a strong correlation of this value, of this quantity, the equatorial compactness at the threshold to collapse, with the maximum compactness for stable TOV models. this is, of course, a little bit far-fetched to say that there is, because we only have mainly 3 points, that there is, it is far-fetched to say that there is a universal value, but the fact remains that there seems to be a very strong correlation between those two quantities. So I will summarize, and what we did was construct massive remnant models with cold equations of state, a realistic differential rotation law, and input for the angular momentum via numerical simulations. We found a very good agreement for the threshold mass value via equilibrium modeling compared to the simulated values at the 1% level. And we also find support for this conjecture that I mentioned earlier in the literature, that the equatorial compactness at the threshold to collapse is strongly correlated with the maximum compactness of non-rotating models. And the most important step forward, of course, is to include the treatment for the temperature. And this is ongoing work, and we are eager to find out how it will change the picture, if at all. Thank you very much for your attention. I'll be happy to take questions if there are any.
Thank you very much, Panagiotis. Any questions for Panagiotis?